Alright, so today we're going to be going over something called the antiderivative. And I think the best way to introduce this is just by first defining it, and then I'll hopefully give you guys some intuition as to what it is and just go from there. So let me just first define it. So d of dx, so the derivative of the integral from a to x, so now x is not some constant, it's a variable, of f of t dt. And notice how this is now, like, because we're using x as a variable, I'm inserting a dummy variable called t over here. But, okay, so the derivative of the integral of f of t dt is simply equal to f of x. And now, this expression shows us, that the integral is simply the antiderivative of f. All right, so that was a lot to take in. So what does this whole thing mean, right? Well, first let's just parse this integral over here. So what I'm doing is I'm finding the integral of this function f of t in some interval from a to some variable x, right? So essentially I'm saying that I have some starting point a, and then I'm finding the integral at some ending point x, which is a variable, and then whatever I get from it, if I find the derivative of that with respect to x, and I can do that, like, because of the fact that this is the bounds, the limits, the lower limit is a and then the upper limit is x, whatever this expression outputs is going to be some function of x. And so when I find the derivative of that, I'm saying I'm going to get back the original function f of x. And because taking the derivative of the integral gives me the original function f of x, we can claim that the integral is the antiderivative. And this, like, just we're like, in plain English, this kind of makes sense because what I'm saying is the integral is the opposite of a derivative, and that's why I'm calling it the antiderivative. And this makes sense over here because when I do the opposite action of the derivative and then I take the derivative, I'm doing like the action again, and then that gives me the original function, right? So, like, let me just showcase this another way. So if I have f of x, right, and then I'm doing the integral, it takes me to some function capital F, okay, so this is capital F of x plus c. Oops, okay, so let me actually make more space. So this takes me to some function, so this operation of an integral takes me to some function capital X, f of x plus c. And the reason why you have plus c over here is because all I'm saying, like, what I claimed is taking the derivative gives me back f of x, right? And the derivative of a constant c is 0, right? So I can have any sort of constant over here. But the idea is if I take this derivative, I get back f of x, right? So if I apply d over dx, taking the derivative, I get back f of x. And so because the integral, so because this arrow, I'll call this the integral, because this arrow of this operation of the integral takes me to some other function f of x, and then taking the derivative of that f of x plus c function gets me back the original function, you can kind of call the integral operation as the antiderivative operation because you're doing the opposite of the derivative, and then doing the derivative again takes you one step closer, right? And so this notion of this capital F of x function is actually very important. So in other words, when I take the integral from some lower limit a to some variable upper limit x of f of t dt, the function that is outputted through that operation is some capital F of x plus c. And I told you guys why you need that plus c, because the derivative of the constant is just 0, and so this expression can be true for any constant c, right? And like one reason or like one way to kind of like make sense of this idea is remember what the integral operation does, right? So if I had some graph over here, right, and it looked like this curve, right? And the integral operation is basically saying that, okay, I'm going to take an infinitesimally small slice of this curve and then find the area that it calculates, right? That's what the integral operation is doing. And then it's summing up all these different slices and it's giving you a final value. And so that's what this like f of x, big F of x function is going to output. It's going to output the slices, the area of all of those slices, and then plus some constant, right? And so if I were to take the derivative of that function that outputs the slice, right? So d of dx at some value f of x, right? Now think about like the slice at x, right? You can kind of think at some value x, the amount I'm adding to the area kind of corresponds to the height, right? And the height is simply given by f of x. And so it kind of makes sense that the derivative of the integral function, or so the derivative of that antiderivative, and the antiderivative is giving us the area up to some interval x anchored at some value a, right? That the notion of that derivative is simply like the change in area at x, right? And the change in area at some point x is simply the height of that function, right? That's how much we're adding to the total area. That's how much we're adding to the total area at some point x, right? Whatever value f of x is takes on at that point, that's how much we're adding to the total area. And so it makes sense that the change in total area at some point x is simply equal to the value that the function takes on at the point x. And so that's another sort of view of the antiderivative, and that's if that makes more sense of why the integral is the antiderivative of f of x, because taking the derivative of the integral will simply give back like the change in the area at some point x, and the change in the area like at some instant at x is simply the height at x. So that's the notion of the integral being the antiderivative of the integral being an antiderivative. And so actually this whole idea has an important observation that we can take from it. So remember how I expressed the integral from a to x of f of t dt is equal to some big F of x plus c, right? Now we know that the integral from a to a of f of x or f of t dt is simply equal to 0, right? And so using this other notation that we established before, so that means that 0 is also equal to f of a, because we're simply substituting x equals a over here. It's equal to f of a plus c. And now we can solve for c. And so c simply becomes negative f of a, okay? And so now we can put all of this together, and then we've just solved for c, and we know that the integral from a to x of f of t dt is simply equal to big F of x minus f of a. And this is very important, right? This means that we can evaluate the definite integral of f from a to any arbitrary number x by simply calculating the antiderivative at x and subtracting it from the antiderivative at a, right? And if we think of the antiderivative as like an area outputting function, right? This function big F outputs the area up to like point x, right? It's simply saying that like if we want to calculate the area from a to some interval x, we simply we can simply take, right, the area up to x, right? And that's what the antiderivative function gives us, like the area from like some negative infinity all the way to x. And if we subtract off the area that is common from a to negative infinity, so if we subtract off, let me find a different color. If we subtract off this portion, right, we're left over with just this. And that's what we wanted from the integral, just the area between a and x. And so what I've shown you is that all of these like terms make sense. And so this part over here is very important. It's saying that if we want to calculate the integral from a to x, and we have the antiderivative function. We still don't know how to find the antiderivative function, but we'll find out all of that later. But if we have the antiderivative function, we can simply take and evaluate the antiderivative function at x and subtract off the evaluation of it at a, and that'll give us what this thing evaluates to. And so another way that like you'll see people commonly write this, and I'll be using that notation later on, especially once we get to evaluating and finding how antiderivatives, is this. And this I can kind of use a dummy variable over here, so for clarity I can just use f of t. But this notation of like me drawing this bracket from x to a just means it's the same thing as f of x minus f of a, but it's just a shorthand. So the shorthand is just the same thing as this. So hopefully that shorthand makes sense as well. And so now that we have that, let's go do an example. And so when we do this example, I'll call this example 1. Find the derivative, or sorry, the integral from 0 to pi of sine x dx utilizing antiderivatives. So we know that like if we were to just ignore these limits, right? We know that like from a to some x value of sine x dx, and d dx of that is simply equal to sine x, right? What do we know about a function whose derivative becomes sine x, right? So let's just treat this as like some capital F of x, right? Because we know that this equals to some capital F of x minus capital F of a, right? And then d dx of capital F of x minus f of a, and this is a constant, so we can just ignore that. So what function has the derivative that equals sine of x? And so we don't have to look too far to realize that the derivative of cosine x, right? We know that d dx of cosine x is simply equal to minus sine x. So the derivative of minus cosine x is equal to sine x, right? So by that pattern matching, we know that d dx of minus cosine x is simply equal to sine x. So we know that capital F is simply equal to minus cosine x. And so now we know what capital X is, or capital F is, and we know that x is pi. So we can evaluate this integral by simply doing minus cosine of x from 0 to pi, because a was 0 over here. This is 0, and then x was equal to pi. So that is simply minus cosine of pi minus, and then minus cosine of pi 0. We don't want to mess up our signs, right? So this is minus 1, and then cosine of pi is -1, so this is +1, right? And so 1 plus 1 is simply equal to 2, and that is our answer. And so I think like the most important takeaway about antiderivatives is how we kind of landed at the fact that this integral, the function big F, corresponds to minus cosine x because of the fact that we use the property of the integral being an antiderivative. and using like what we knew about the derivatives and knowing how cosine maps to minus sine x to find out how the antiderivative function was actually minus cosine x, right? And so that's actually, as we do more and more complex integrals and we have to evaluate them, we'll go back to our knowledge of derivatives and see how that leads us to know what the antiderivative function is given whatever the integrand is. And so that's basically like how we'll tackle most of the integral problems. And obviously there'll be some tricks along the way that will help us as well. But the idea and the notion of the integral being an antiderivative is one of the most important things.